Okay, let's talk about Riemann sums and definite integrals. The objectives for this section is to learn what a definite integral is, right? Talk about what the integrand is, limits of integration, variable of integration, so basically what the bits and pieces are of it. How do we decide if something is integrable? And look at some relationships between like total area and net area and average value theorem ultimately. Okay. First things first, there's 2 notes here. I just want to make sure that we're aware that when we were approximating the area under curves with rectangles, that it doesn't have to have the same width for each rectangle. So the whole idea of infinitely many rectangles applies even if the width of the rectangles isn't the same for every rectangle. Because ultimately all of the widths, regardless of if they're the same size or not, are going to 0 as the number of rectangles goes to infinity. So, and next, we approximated the area. If we, whoops, typo, have infinitely many rectangles, our area would not be approximate. So when we take that limit, it's no longer an approximation. Okay. So what do I mean by that? Oh, I did not mean for that to go and do that. Okay. If we look right here, this is what we're talking about. We learned in the previous section that this represented the height and this represented the width of each rectangle. Okay. We're adding up all the intervals, or all the rectangles areas, right? This is the area. And we're adding them all up. How many? Well, we're taking n going to infinity. So we are taking infinitely many rectangles. Okay. All right. So it's kind of like picking apart what we're working with there. And then we also have the definition here of a definite integral. So a definite integral, if you picture this notation, this, we learned that the limit of a sum was an integral. So what I am doing here is I'm looking at the sum from A to B of a function, right? And so that's what this is, because we are looking at all of these rectangles, heights and widths from here to here, and we're adding them all up. There's infinitely many of these rectangles, and we're adding them up. So a definite integral is basically the area under the curve from A to B. And actually, I mean more than basically. Okay. We'll actually do a limit by hand before we learn how to do any shortcuts with the integral. All right, what's what inside this integral? The integrand is the function, okay? The dx that we were using delta x for at the back end, that's telling us what the integral is with respect to. It's our indicator of the variable of integration. And it doesn't have to be an x. Could be a t, could be a u. It's just a placeholder, okay? All right. Any function, I'm dumping down to the theorem now, any function that is continuous can have an area under it. Issues you would have is if it wasn't continuous, how would you find the area under it when you have a gap, right? So, or even a jump in the graph. Let's look at this first example here. Let's kind of wrap our head around all the information that I just spewed out. we're going to use the definition of the definite integral, which means we are looking at the limit as n goes to infinity of the sum from one rectangle to infinite rectangles. Okay. What is the function? So right here is that f of x part. Okay, so these are the pieces that we have to take care of or fill in. Well, the function's x squared, but I have to be careful because they want me to use right endpoint approximation. So we are essentially looking at from 0 to 2, 4, right? And we're using right endpoint approximation. And they're not telling us what our delta x is. So let's establish delta x, okay? Delta x is going to equal, well, we have 2 units of width. So we just take, 2 minus 0. And we're dividing it into n subintervals. We don't know n, right? In fact, it's going to infinity, so it's huge. So the width is going to be really small. Okay. F of x piece. How is our, for each one of these widths or each one of these rectangles, how are we calculating the height? Right? Well, if we're going to do, I'm just going to show you with 2 rectangles, but we know we have way more. And if we're doing right endpoint, right, that means that this value here is how we would calculate it, right? Well, if I just had 2 rectangles, I'm calculating it at 1. If I have 4 rectangles, I'm calculating it at 1/2, right? So how do I decide where the first one's going to happen? Well, the gap, the width for every rectangle, we've already established. The first rectangle is going to happen at the function's value squared. Now, the first rectangle's height is not happening at 0. It's happening at 1 width over, right? So it's not happening at 0. It's 1 width over, 2 over n, okay? Now, I have to be kind of careful here because when I plug in a 1, I need to get the first rectangle, whatever it may be, right? So if I put in I here, will that give me the height at the first rectangle? Yeah, because your first x input is going to be, let's get these gone. Your first x input is going to be 2 over n. The next one is going to be 2 over n twice, right, for the second rectangle. And then so on and so forth for the other ones. So I like this. You don't need to put the plus 0 if you know that. So that's your f of x piece times your delta x piece is 2 over n. Okay? Now, ultimately, I need to evaluate this. And this is where it gets, well, the setup is tricky, and then to do this limit business gets tricky as well. So here's what we're going to look at. We learned in the previous section, and go back and look at it if you forgot, we learned that things we can manipulate, and we learned some summation rules. Okay? I don't need the 0 there, so I took it off. This right now is basically, oops, let's get rid of that negative, 4 over n squared times I squared times 2 over n. So in other words, 8 over n cubed times I squared. And we're going from an I value of 1 to n. Okay, 8 over n cubed is a constant. Okay, I'm plugging into the I spot. That's what this says down here. I'm plugging into the I spot, not the N spot. So I'm not going to do anything with the 8 over N cubed. I do have a formula, though, for the I squared when you run it from 1 to any number. We learned it in the previous section. It was N times N plus 1 times N times 2N plus 1 over 6. Okay. When I see this, here's what I see. I see, I don't really care about the small potatoes, as I call them with my seated class, but I care about the leading coefficients, okay? So leading if you multiplied it all out, well, actually, there's an N here and 1 here, so now it's an N squared. So I have 8 times, and if you multiplied this all out, you'd get a 2N squared plus N plus 2N plus 3N plus 1 over 6N squared. Ultimately, and we're taking the limit of this, so ultimately we have 8 over 6 is a kind of a coefficient, and you think about the limit of that, you would see that that limit is 2. So ultimately, in the end, simplifying this, we would get 8/3 by taking the limit, which is the definition of the integral. Those are kind of tricky. Okay, so we visit it for a little bit and we kind of move on, but it is the fundamental reason why we get to make these other shortcuts. Okay, next one. This time they're like, hey, you don't actually need to do the limit process. You can just look at the graph, okay, and then decide, because this is going to be a circle when we graph it, but I'm going to show you why it's a circle. The function is y equals the square root of 9 minus x minus 3 squared. Square both sides. I'm going to add the x quantity piece to the other side, so it would be a positive x minus 3 squared plus y squared, and then a 9 over here. Well, this is a circle. Hopefully you recognize it now as a circle with a center at 3, 0 and a radius of 3. Now, I don't want the area of the whole circle, okay? It says use the formula of area to evaluate this. We want the area. Now, it's a positive y, okay? Why? Because it was a square root, so that's the answer there is a positive number. So the circle itself is like this. However, this function is only positive values, so we'll take that part of it off, okay? And then the next part says we're just going from 3 to 6. So actually, we don't need that part either. This is 1/4 of the area of a circle. So 1/4 pi r squared. Hey, r is 3 here. So we're going to get 9 pi over 4. It's just area of it, so units squared. There you go. All right, that one wasn't so bad, hopefully. Okay, we're going to talk about net signed area. And by signed, we mean there's positive areas and there's negative areas. If you look at this picture, the difference is what's above the x-axis and below the x-axis. If it's above the x-axis, we consider it a positive area. If you're running it in numerical order, so if you're running the integral from 0 to 1, you're going to get that positive area, okay? If I'm running the interval from 1 to 2, and the graph is below the x-axis, then this is a negative area, okay? So net area is when you add the two areas together, stuff below is a negative, right? Or it's subtracted off. So if this was 4 and this was -5, the net would be the sum of those two added together, okay? So it would be -1 net. Okay, so I don't know if that's what that is, so don't quote me. I was just throwing numbers for an example. Go here, find the net signed area between the curve from -3 to 3. 2x. So when I plug in a 3, I get 6. Plug in a -3, I get -6. Okay. Now, it's always the area between the x-axis and the function. So that's supposed to be where the 3 is. Okay. So this area is 1/2 base times height. So 9. And this one is 1/2 base times height, but it's negative because it's below the x-axis. So we can break this up and we would say we're looking at the area from -3 to 0 of our function is -9. And the area from 0 to 3 of our function is a +9. So when they ask for the net, you're adding them together. It's a net 0. Okay. Now, why do we like this and care about the signs? Although total area here, if you weren't doing signs, your total area would be 18, but you would compensate by putting an absolute value on the function if you wanted that. Okay, kind of a lot here notes-wise, but excuse me. But take a look at these with me. This is the velocity graph, okay? Velocity versus time. If you go 70, and this is the graph of velocity, if you go 70 miles an hour for 2 hours, there's your velocity curve function, okay? Now, check this out. If you are going for 2 hours at 70 miles an hour, you have gone 140 miles. If you look at this picture, you will see a rectangle, so area under the curve is distance traveled. You went 70 for 2 hours. So point is, now I'm going to contradict myself here. It's either distance traveled or displacement. Okay, let's look at a displacement example. Okay, in the and that allows you to take if a car travels straight north at a speed of 60 miles an hour for 2 hours, the area under the curve is 120 miles, right? If you think about this, this is 60 miles an hour. That's the height. And you're going to multiply that by the number of hours. Miles per hour by 2 hours. Labels cancel like numbers do. You have yourself 120 miles. Okay? All right. Next, if the car then turns around and travels south 40 miles an hour, okay, velocity is speed with direction on it. So now we're at negative 40 miles an hour for 3 hours. So basically you went down or south 120 miles. Now, if you add these together, you get 0. That is displacement. Displacement is how far you are from your original position. If you think about this on a number line, you think about I don't know, elementary school. Add 2 minus 3. Add 1 minus add 6 minus 8 plus 3 minus 1. Ultimately, where are you at with regards to where you started? That's displacement. Okay? All right. So displacement is 0. You're right back where you started. Total miles traveled, we would have to break it up into the two pieces. Okay? Total miles traveled, we would have to go, well, let's do an absolute value of the velocity equation. Then it would pop this up into positive territory and you would have total miles traveled. When you are going and then going back, you're doing displacement. All right. And that's what this set box says right here. If you wanted total area, you'd have to break it up and do the absolute value. Okay. Let's go here. Find the total area between f of x equals x minus 2 and the x-axis over the interval from 0 to 6. Okay. Best way to do that is to draw a little sketch. So I'm going from 0 to 6. If I plug 6 in here, I get 4. If I plug 0 in here, I get negative 2. Okay. It is a line, a slope of 1. So actually, 2, 4, 6. Okay. Total area. If I was going to do total area, I have to break it up because I want this piece to be positive so that when I add the two areas together, I get 2 positive areas that I can add together. Really don't overthink it. You know, we can break this up and go 0 to 2 of x minus 2 dx. That's that piece. And we want to add, I have to be careful here. I'm going to have to put a sign in here, so I'm going to change it in a second. From 2 to 6 of x minus 2 dx. Now, I know that this is going to return a negative number. Now it will return a positive number. So for this region, I want the opposite of, it's below the x-axis, so negative 1/2 base times height. So in other words, this is going to be an area of 2. Let's go in here. This one is positive. I know I'm going to get a positive 1/2. Base is 4 units. Height is 4 units. And we get 8. So total area is going to be 10. total displacement, or displacement rather, would have been 6. Okay? All right, rules of integration. So these are rules, they actually are really similar to like regular function rules. Like, can you break them up and evaluate 2 different functions before you add or before you subtract? Like a function with multiple terms. Yes, you can. Yes, you can. If this one's number 2 is interesting, and that is we typically run our integral from smaller number to larger number. But if those are flip-flopped, then you get a negative value. So you will get the opposite. So we like to go small to big, right? So here, basically, if you think about it, it's left to right on a graph. So if you go left to right, you'll get a number. And then if you switch it and you go right to left, you're going to get the opposite of that number. It's probably an easier way rather than small to big. Okay? This top one, if you don't actually go anywhere, so here's your function, right? But you're at A, starting at A and ending at A. Are you going to have an area? Nope. Okay. If you have a constant, you can pull it out front. And this one, I actually kind of have hinted to it. I can break it up into the same function here, but into multiple pieces. So here's a kind of a picture. If this is A and this is B and C is somewhere here, I could go from A to B and find the area. Or I could go A to C, find the area, and then C to B and find the area. It's going to be equivalent. Okay? So with that in mind, let's go to 5 here. If it is known that the integral from 0 to 8 is 10 of f of x, excuse me, and the integral from 0 to 5 of f of x with respect to x is equal to 5, find 5 to 8. Well, visually, if we know 0 to 8, say, and we know, and all of that is 10, we'll do it this way. That's all 10. And we know 0 to 5 is 5. Then what are we doing? Taking the area of 10 and we'll take 0 to 5 off of it. And if I take 0 to 5 off of it, what's left? Well, then what's left, this will be gone, and the only thing left will be this piece right here. In other words, it's equal to 5. Okay. All right, comparison. This is actually kind of silly, and if you graphed, I'll draw a little sketch of both of these. And it's not really silly because in math we have to prove or show everything before everybody just buys into it. And sometimes we take the time to prove it, and sometimes instructors don't. But everything that has been established mathematically has been proven, or there's corollaries to a proof that exists for something similar. So, okay. So here, let's graph each one of these. What does f of x look like from 0 to 1 versus g of x? All right. If you graph this, and you're free to do it with your calculator if you want, f of x is going to do something like this, where it kind of swoops down and then up. And then g of x is going to look something like this. So this one is g of x. This one is f of x. Okay. Excuse me. Here's the interval 1. They have the same value. When you plug in a 1, you get square root of 2 for both of them. So they intersect here, they intersect here. Okay. It's clear that in this interval from 0 to 1, g of x is greater than or equal to f of x. Okay. Well, if you think about this in terms of the area under the curve, the area under the g of x curve is there. The area under the f of x curve is there. Is the inequality preserved? In other words, is the integral from 0 to 1 of g of x, that's the yellow highlight, larger than or not even or equal to, but larger than or equal to the integral from 0 to 1 of f of x dx? Yes, so basically all we're saying here is that integration preserves inequality. So if something is greater than or less than, it will remain that way. Okay. All right. We're getting closer to the end. Average value. You know, when we were talking about the velocity function and we graphed velocity and it was a consistent velocity the whole time, what's the average value? The average value is 60, right? Well, if you had, what was it? Was it 60 over 2 hours? If it was 60 over 2 hours, the distance was 120. Now think about this. If you knew the distance was 120 and you wanted to figure out on average what the velocity was, you would divide it by, your change in x, right? So you take your area and divide it by your change in x, or in other words, the gap from A to B. Well, how do you find the gap? Well, you subtract B minus A. So that's what this is. Now, not everything is going to be a perfect rectangle, right? Let's suppose you started at 0 miles per hour and you ended at 0 miles per hour. So you sped up, then you slow down, right? Nice and smooth like that. Obviously, the velocity is changing the whole time, but what if you wanted the average value? Well, we would do the math the same way. You would find the area under it and divide it by whatever the max change is for x, right? So that's what this is. This is basically over the span, and this is the area. Okay, so if I take this, you see that from 0 to 5, 0 is a 1, and 5 produces a 6. So it gives us a trapezoid shape here. So I want to find the average value, the average value of f. So we could do this 2 different ways. Here's the way we're going to do it right now is we're going to say, okay, well, my gap is 5 minus 0, so 5. And obviously the value is changing. What's the average value, right? So that is the gap. And what is the area? And that is from 0 to 5 of x plus 1 dx. Okay, now what is this? Well, we know it's area under the curve, and this is a trapezoid, right? Do you remember the formula for the equation of a trapezoid? One half. We said B1 plus B2 back in like middle school, right? Times height. But your B1 and B2 are the 2 parallel sides. So for us here, this was a height of 1. It's a 1 plus a 5 times a height of 5. And I misspoke here. It's 1 plus a 6, because what's the height here? This was a height of 1. This one had a height of 6, right? So I got to fix my typo. This is B1, B2. All right. So 1/5 of 1/2 of 35. Right? 1/5, 1/2, 7 times 5. All right. Simplify that, we get 5/2 for total. For average value. So that's the average value here, is 2.5. Okay? Last thing to mention, and that is you have done indefinite integrals. What I showed you today was definite integrals. There is a difference between the two, okay? So a definite integral is a number, like the problems that we just worked with. Here's an example. 0 to 1 of 2x dx is the area under the curve. So area under the curve, 1 height of 2. So the answer here is 1/2 base times height, 1. Answer is a specific number, okay? This is a definite, okay? Versus indefinite, okay? Here was an indefinite one. No start, no stop, indefinite, okay? Remember when we were doing antiderivatives? We would raise the power, divide by the new power, plus a c at the end. So this was x squared plus c. This is a family of functions. A definite integral is a numerical answer. An indefinite integral is a family of functions because you don't have a way to evaluate, right? There's no start and there's no stop. So it is, like, these are the results, okay? That concludes this section.